Hello, I'm David, and these are David as well, and I'm the coordinator of the Maths Learning Centre. Welcome to Semester 1, 2018, those of you from the future, and welcome to all of you who are actually in the room. That's enough of that, as fun as it is. Right. This is the Engineering Maths IIA revision seminar. And I've been asked by several people to talk about probability, and so I will. I'm mainly going to focus on probability distributions. If you have a desire for me to talk about general probability, please feel free to ask when I say, do you have any more questions? All right. Right. So, okay. Now I have to decide what I'm actually going to say. I have been thinking of it on and off over the last week, but now I have to make a decision. Probability is the mathematician's attempt to deal with things that aren't always the same. And any time we calculate probability, we're trying to figure out some sort of idea of how often something happens or how much we believe in whether it's going to happen. So that's the basic idea. So how often things happen and how strongly we believe something might happen. And human beings in general have five type measures of probability in their head. We have impossible, absolutely certain, roughly 50-50, and somewhere in between. You know, it's more likely to happen than not happen, or it's less likely to happen than not happen. And that's pretty much it. So if you're thinking probability in everyday language, that's pretty much all the options. But mathematicians like to have this sliding scale from 0 to 1 of all possible numbers in between. So impossible is 0, 1 is always happens, and everything in between is a thing. And the reason I think of that is that even if you as a human being are only able to say, well, this is sort of more likely than not likely, it is technically possible for you to take two events and decide which of them is more likely. And so that is sort of indicating that there's probably a number in the background somewhere that your mind is working on, or at least that you can turn it into a number if you want. So it's technically possible for any two events to decide which of them is more likely. So there might be something here, you know, A and less likely, more likely, something like that. And there are some things that are equally likely as each other, and that's all great. So I'm really just talking until I think of something good to say, so just bear with me. So that's the sliding scale of probability, and anything that I could care to name that might or might not happen would have a number somewhere between 0 and 1 to describe how often it happens. That's good. To go a little further in this, when I think of a specific event, like rolling a die, for example, there are actually multiple different things that could happen. And each one of them has a probability of its own, and the only reason why any one option on a die has a probability is because the other options are there. So it may be that I might have several options for what could happen, and each option has a probability. And the thing I like to say is the only reason why anything has a probability is because everything has a probability. So usually, if you're thinking about probabilities, you don't want to think about just the thing that you're interested in happening. You want to think about all the things that could possibly happen and compare yours to those. So that's the thing that's in my head. Okay. So all things that could happen, and compare your event to those. That's the idea of probability. I don't know if it's important to write these things down, but if you didn't want to watch the video, you could just, get the notes and it would remind you what I said. So, okay. So these three ideas are the ideas in probability, and these two here are about, this one here is specifically about the idea of a probability distribution. So probability distribution is saying, it describes all of the options that could happen and how likely every option is. So it describes all the things that could happen and how likely they are. And there are some technical details that we'll get to later. If I forget to mention them, then feel free to ask me. David, did you mention those technical details? So there are some technical details we'll get to later, which come from the fact that if there are infinitely many options, it's a bit tricky to talk about how likely they are, but we will get to that. Okay, so that's what a distribution is. And all probability problems are actually secretly about distributions, because no probability exists independently of the other things that could have happened. So if I pull a card out of a deck of cards and I say, well, is it an ace or not? Well, there's two things that could have happened. It could have been an ace or it could have not been an ace, and the only reason there's a probability of there being an ace is that it's possible for it not to be an ace as well. So you actually need to think about all the things that could happen in order to figure out a probability. And that's my first piece of advice. Okay. So, luckily, mathematicians and statisticians have been thinking about the idea of distribution for quite some time, and they have come up with a list of useful distributions where if you say the name of the distribution, then for someone else who knows what you're talking about, that's enough information to tell you everything you need to know about what the possibilities are and how likely they are. Cool. Right, let me just start off with a neat little example. Rolling a die. And the options are 1, 2, 3, 4, 5, and 6. And each of those options has a probability of its own. So I should call it x for the number that could happen, and the probability of x. And if your die is arranged the way a die should be arranged, they all have the same probability. And that probability should add up to 1. Because all the things that could happen together happen. And so 1 is the probability of something happening. And normally you draw it as a diagram, right? You'd go 1, 2, 3, 4, 5, 6, and they all have this probability, and the height represents, there's a y-axis here, and that's 1/6 there. Cool. That is the distribution of the roll of a single die. Now, the distribution of a roll of 2 dice is a bit different to that, and it has its own distribution. But I'm not going to do that. I'm going to do getting an even number on a die, right, on a single die. And the options are, it could be even or not even. And they both happen the same chances. They're both a half. So it doesn't technically have to be a number that comes out of your thing. You can think about these are the options, even and odd, and this is how likely that they are. They're both half, equally a half each. Great. All right. So the first point I want to make is that the same situation of rolling a die, depending on the thing that I'm interested in, has 2 different distributions. This is the distribution of the number itself, and this is the distribution of the even and oddness. And anything that you could anything about a situation that you could write down would have its own probability distribution. And that's important because there are some important situations that come up in Eng Maths IIA that are the same situation measured in two different ways. Sweet. So this is lovely. I can argue this out, but some situations are a bit more complicated than this, and we have to rely on the wisdom of those who've tread this path before us to have done the calculations that are required. So, excellent. I am now going to run through the list that is on your Engineering Maths IIA formula sheet that is supposedly coming in your exam, and talk about each of the distributions in turn. And not just talk about the stuff that's on that table, because you've got that already, but also talk about the stuff about where they come from and what situation they fit with. Okay. So let's see. Oh crap, before I do that, sorry, I did want to say one more thing. If the thing that happens produces a number, then there are two things that you can do to give you a handle on how the probabilities are spread out here. And they are the mean and the standard deviation. And I really should put that higher up. So, or the variance, if you like. If my describes numbers, then the official name is random variable. Then you can calculate the mean and the variance or standard deviation. And a mean is some sort of idea of what you would expect to happen on average. And the variance is some sort of idea of how the probabilities are spread out. And so whether most of the things occur, most of the numbers occur close together, or whether they tend to be more highly spread out than that. Okay, so the mean is also known as the expected value. Not to say that it will actually ever happen necessarily. The expected value on a roll of a single die is 3.5. You can't roll 3.5, but if you roll a die 10 times, you expect it to give you 35 as the total, which is useful if you're designing a board game. So that's the expected value. It's sort of like, you know, where the possible values tend to be centered. Center of the possible values taking into account how likely they are. The likelihood. And the variance is some sort of measure of how spread out they are. How spread out the probability is. Okay. The reason we care about variance is that, well, we like a number to say how spread out it is, but also some distributions, all I need to know is the mean and the variance, and I know everything I need to know about the distribution. And so the definitions of them are, you have to somehow add up, to do the mean, you somehow have to add up all of the possible answers for your number, taking into account how likely they are, so that things that are more likely end up in the average more, and things that are less likely end up in the average less. And so for, I'm going to use words that I haven't talked about yet, but the mean would be something like the sum of each of the values times the probability that it comes out to be equal to that value. for all the possible x's. And if this were, yeah, I'm just going to leave it at that. And the variance would be the sum of all of the squared distances from the mean times their matching probability. That's the definition of what they are, at least if it's possible to add up all of the x's separately. So something with like a die where there's only like separate numbers that it could be, that's how you would do it. But if your number is able to produce anything within a zone, like it produces all the numbers from like 1 to 5, including 4.999 and 2.876 and no matter what decimal you like, then those sums will become integrals. So this is what they call the discrete version. And the continuous version, they'll be integrals. And for some reason they switch it from P to F when you do continuous ones. I should probably talk about that actually before I get into it, really. Damn it. Sorry. This is what happens when you make these things up as you go along. But luckily I'm not actually your lecturer and these are not the actual lectures, and so you had hold me to a different standard to your lecturer. Now, if this is what happened in your lectures, I don't know if you'd like it very much. I remember one of my third-year maths lecturers was in the middle of a proof and went, "Oh man, I forgot to do a lemma that we needed to do this proof," and so he went back and for 2 lectures did the other proof that he needed to do this proof, and then he came back to the proof we were doing and started in the middle of the sentence he had left from and continued from there. Man, that was bad. So, anyway. Yeah. He was interesting, that guy. So I should probably talk about what I mean by discrete and continuous. And the only reason I really need to talk about it is because of these things happening. So a discrete variable has only specific numbers that it can be, and those numbers have gaps between them. This is my definition. I'm sure there's an actual definition for this. In general, it means that they can only be whole numbers. Okay, but it is possible to have a discrete variable that can only be 1/2, 2/3, and 5/16. But specific numbers with gaps between them. Okay? So at some point when you pick 2 particular numbers that could happen, you get down to a point where it's impossible to get anything between them. So e.g., you can only have 1, 2, 3, 4, 5, or 6. Or, 0, 1, 2, 3, or anything up from there. Or, 1/2 and 5. Who knows? It could be any specific numbers with gaps between them. Okay, and their distributions as a graph look like this. Whatever they look like. Might be something like that. For example, this one here might be really likely to have nothing and then gets more and more and less likely as you go along. And here the height represents probability. Okay, then you could have continuous variables, in which case it's like any real number in a zone. Let's say domain, that's the official word. Any real number in a domain. Meaning that no matter which 2 options you pick, it's technically possible to get anything in between them. And I can't really give an example for, so e.g., any decimal from 0 to 15, for example, that would be a continuous variable. Or there's ones that like, you know, any decimal x with x is greater than or equal to 0, something like that. They're the sorts of things you can do. You can even have ones that can be any real number at all. Okay? Point being that you can make it as finely grained as you want. And that's where this is not going to be possible, because there's infinitely many possibilities. You sort of go, well, if I compare this one to all the other ones it could be, then it doesn't really account for any of the probability. And so what you have to do is go back to here and think, all right, well, if this width is 1 here, then all of the heights here could have been reinterpreted as areas. And so what I'm going to do now is I'm going to draw something like, you know, that, a nice continuous curve. And now the height doesn't really mean anything. The height is sort of the probability of being near to this spot, but it's now the areas of probabilities. Okay. Sweet. So that's called a continuous variable. And this is like y equals f of x. That's what they'll call it. And that's the f that I was referring to when I did this thing here. So in some sense, that f of x is like the probability of being close to this number, because I could, you know, round everything off to the nearest decimal place, and then it would become discrete, and I can use it that way. But in a way, it's like it's really the derivative of how quickly the probability is increasing as you include more and more things. So if I say, well, let's just include everything below this point, as I include more and more possible x's, the probability here is increasing quite slowly, and the probability here is increasing a bit quicker, and the probability here is increasing the fastest. And so it's more likely to be close to this number than it is to be close to that number. Okay. Which tells me one more thing I need to say, actually, when I'm talking about this, is that statisticians really, and mathematicians really struggle with, I mean, they have names for them, but they really struggle with the concept that this one, the height is interpreted differently to the way this one's height is interpreted. That doesn't make them feel comfortable. And so they actually much prefer a completely different way of describing probability, which is to do the probability so far. So if I can do this thing, just some terminology. The function which says how high this is usually called the probability mass function. It tells you literally how much probability there is, or just the probability function. The function here, which describes how high this is usually called the probability density function. Or PDF for short. This is PMF for probability mass function. And the reason we have to give them different names is because the height of that function tells me different information. One of them tells me a probability, and the other one, well, it doesn't really tell me a probability, it just allows me to calculate areas, and the areas tell me the probability. So what our statisticians do is they go, that's really frustrating. I would like one way of describing probability for all random variables, and their one way of describing probability for all random variables is to add up the probability up to a specific number. So the cumulative density function is like the probability so far. Okay? That's what that is. And so the idea is that they call that capital F usually. The probability that the x's that you could have had, they use a capital X for the x's that you could have had, is less than or equal to the x that you're currently up to. And so the picture is like, if that's x, then that area is capital F of x. And I call this the CDF. This happened yesterday. We think we have a possum. Okay. The reason why that's really cool is that it could actually be that for a discrete distribution, what will happen is, it is technically possible for a die to tell you the probability of being less than or equal to 3.2. Because it's a half. Half the numbers on a die are less than 3.2. And so what will actually happen is that for a discrete one, this is continuous, discrete, it'll go like, oh, we haven't got any probability, and then suddenly we have some, and then suddenly we have some, and then suddenly we have some, and then suddenly we have some. And it'll go like that. And it'll jump up every time one of the numbers that's in your thing actually happens. And this makes our mathematicians extremely happy because now they have the same way of describing both things. And this is one of the reasons why you have to be a little bit careful in MATLAB, because MATLAB can calculate, you know, for one of these, what the probability of being less than 2.5 is. Be whatever it, you know, whatever should be the same as the probability of being less than 2. Crap! Oh, bloody hell! Sorry. So this is the PDF. Oh, for the sake of Frel, David. CDF just keeps going up and up. Like it's this height here is the probability so far. Whereas this one is a CDF. Right, got it. All right. So every time you get to one of these things, that's what causes a jump in the probability so far. All right, let's just make sure that I'm working on this. Okay, that's all well and good. Okay, this stuff will become more clear as I talk about the specific distributions. Okay. So, a list of distributions. And hopefully including the situations in which you would come across them. So, I may or may not put them in all the discrete and all the continuous ones because I'm going to organize them by situation as opposed to by type of variable. So, my first situation is the thing that happened earlier with my die. Any situation can be turned into a yes or no variable if I want to. I can say, I can do something and then ask a yes or no question, and the answer is either yes or no, and there's a probability of yes and a probability of no. And that is what the Bernoulli distribution is about. So the Bernoulli distribution is discrete. And it describes the situation where you take something happening and you ask a yes or no question. So e.g. is the die roll even? Are more than half of these oranges bad? whatever, just making up crap. So any time that you could answer a just straight up yes or no question about the entire situation, that's the Bernoulli. And what you do is you record the answer yes as 1 and the answer no as 0. And each of them will have a probability of its own. So the yes will have a probability of p, and the no will have a probability of, well, it's everything else, so it'll be 1 minus p. And that's the Bernoulli distribution. It sounds pretty stupid, but what it allows us to do is turn any yes or no question into a number, which is nice. Okay, and the thing is, I can now, because it's a number, do the average. So if I roll a die 15 times and I ask, what's the average number of yeses? Well, I'm just doing the average of my Bernoulli distribution. Though I'm not really, because that's a whole separate question. But I can say, on average, what would I expect that number to be? And so if it happened half the time, then the average would be a half. If it happened 2/3 of the time, the average would be 2/3. And so the mean of these numbers turns out to be just the probability of that thing happening. So it looks like this. Oh, they might not be the same. Maybe this is p and this is 1 minus p. Because I've chosen a p that's less than half, it'll look something like that. That's its PMF. And it will go, the mean is p, and the variance is p times 1 minus p. All right, cool bananas. That's the Bernoulli distribution. It sounds stupid, but it does allow me to describe, almost every situation that I could possibly be in. Because I could go, well, let's ask a yes or no question. Bernoulli distribution, woohoo! Okay, so my next distribution is going to do this, but with multiple objects simultaneously instead of just one big situation. The binomial distribution does this, but with a group. So the Bernoulli distribution says one situation or object, we record yes or no, and it's either 1 or 0, and the, 1 might be more or less likely than 0. With the binomial distribution, we do this Bernoulli thing, but for a group. So just so you know, it's discrete. So we record the answer yes or no for n objects or situations. And the official name for this is trial. And the thing that we actually write down when we write down a binomial distribution is how many yeses there are. Or no's, it doesn't really matter, but we're going to say yeses. So x equals the number of yeses. So this is the picture in my head. I do it with people because I normally do medical statistics. But here we have a whole lot of people. And each of them has a yes or a no. And then the binomial distribution records a piece of information about the entire group. And it says that the answer is 1, 2, 3. That's the number that comes out of my binomial distribution. How many yeses? And in a different group, I might have gotten a different number. So this is a big key thing I want to point out to you, is that even though for each individual single person it's a Bernoulli distribution, which just says yes or no, when I take it as a group and I'm talking about how many said yes in the whole group, it's a different distribution because different things can happen. So in this one, with a group of 1, 2, 3, 4, 5, 6 people, I could have none up to 6 of them saying yes. Just a second, 1, 2, 3. And it's sort of most likely to have the one in the middle. Tends to look like that. That's my PMF. And that'd be great, and it would technically be possible to actually calculate this by hand every single time. But the whole reason we have a name for this is so that we don't have to do all those calculations, and we can now start to say, just a second, is there a formula that tells me how high this is? And yes, there is. The formula is that the probability that my x comes out to the specific little answer of little x is, just a second, I'm going to need one more piece of information. Record answer yes or no for n object situations trials, and for every one of these objects considered individually, it's the probability of p of getting a yes. Probability p, yes, for one object by itself. Okay. So it's this. Crap of all crap. N choose x, p to the x, 1 minus p to the n minus x. And that is the probability that describes the height of each of these things. So when your thingy here says that the parameters are n and p, they are the two numbers in my formula here that I need to be able to figure it out, including, I need my x obviously, but it'll be different for different sizes of groups, and it'll be different for different probabilities of success. And so it's the n and the p which tell you which binomial distribution you have. Your lecturer, do they call this B or bin when they write the notation? Bin, okay, cool. So you can have some notation. You'll say x is distributed according to a binomial distribution with n and p. So that this symbol here means is distributed according to. And if you told a statistician, and now you guys, this piece of information, you would automatically go, oh, okay, so this must have come from recounting how many yeses happened, and there are n objects in the group, and the probability for one of them is p, and actually the formula for the probability is this. This encodes all of that information, and that's everything you need to be able to tell it. So when a lecturer says, what's the distribution, this is the sort of thing they want you to say. And so that I can fit it all on one page, the mean is n times p, and the variance is n times p times 1 minus p. This mean is actually not that hard to believe, because the mean is what you would expect to happen. So if you expect something to happen 50% of the time, and you've got 6 people, you would expect 3. Which would be 6 times 50%. So I should probably do some examples on that. But maybe I'll get to them later. So this is literally how many you would generally expect in a group of size n. That's what you're doing. Number expect in group of size n. Okay, there are some specific rules that you might want to look up. It's very important to realize that in the binomial distribution you have to choose how many objects there are in advance. You can't, for example, count how many yeses Like you can't say, how many times do we have to do this until we get a yes? That's a whole different distribution. We have to specifically choose how many they were looking at to start with, and then count how many within that come up with yes. That's the binomial distribution. If you have some other situation, then it's not necessarily, well, then it won't be binomial because it's not counting the right thing. Okay, so I can create a binomial distribution from any situation, as long as because I can create a Bernoulli distribution from any situation. So anytime I answer a yes or no question, that's a Bernoulli for the single object, and then I answer a yes or no question for a group of objects, suddenly it's binomial. And I can even create a binomial distribution from a continuous distribution if I want. It's a classic exam question, which I will talk through at some point, but I won't be able to do it until I do some other distributions. So that's the binomial distribution. Okay. That's as far out as it goes. All right. So I might go this way. Right, I want to switch over to continuous distributions now for a minute. I'm going to skip the Poisson, which is on the list, and come back to that. So, right. So we've already had a switch of perspective once here. We had single objects and then groups of objects. And now what we're going to do is go back to single objects again. Yeah, no, I'm going to do uniform, sorry. The uniform distribution is for when you have a number and it can be anything between here and here, and that's basically it. Technically, you can have discrete uniform distributions as well. Like the roll of a die is uniform, but in this course uniform means continuous. So it's continuous and it can produce anything from A to B, including all the decimals, and everything is just the same likelihood as everything else. So if you ask your computer to produce you a random number between 0 and 1, that's a uniform distribution. You want everything to be equally likely. And x is just the number you pick. Okay? So let's have a look at the graph. My PDF, here's A, here's B, everything's the same likelihood. Now you don't actually need any more information than this to figure out anything. Like you can find a formula for the height of this, but it's not necessarily something that you need to remember. Because the idea is that you know that the total area has to be 1. So since the total area is 1, and this width here is B minus A, therefore the height has to be, well, 1 divided by B minus A. That's a very bad brace, I'm sorry. So if you had something that was between 2 and 3, then the height would have to be 1, because the area has to be 1. So if it's 5 wide, it must be a fifth high, so that when you go 5 times a fifth, it comes out to 1. And if it's 17 wide, it must be a 17th high. And if it's a half wide, it must be 2 high. Basically, that's the idea. Okay, I'm going to go over 2 pages with the uniform, I'm sorry. So when we do this, that means that the PDF, f of x is just 1 over b minus a, regardless of what x is. I mean, technically, it's 1 over b minus a if x is between b and a. X is between b and a. And it's 0, outside. No, what's the official way of saying that? Otherwise. Not that we care what happens out here, it's just this bit here. So that's why this thing here says, look, there's the 1 over b minus a. But I was totally able to figure that out all by myself. I didn't need to remember that or look it up. Okay, so while it might be possible to calculate might be totally possible to calculate a mean and a standard deviation, that's actually a lot less useful than just literally being able to calculate the probability between two things. So I'm actually going to do an example for this one. I'm going to tell you what the mean is. It's just the average of A and B, and the variance is A minus A squared on 12, just because that's what it is. I'm sure there's a way of proving that. And if this was an entire course on probability distributions, you would probably be a classic exam question to prove that that's what the variance is. But you haven't been asked to prove things in this course, so I'm pretty sure that won't be there. But I just want to do an example. Suppose y is a uniform distribution from 3 to 7. Find the probability that y is between 2, maybe I should pick a number that's actually in the range, 4.7, 6.5. Okay, cool. So the easiest way I know to do this is just to imagine what that looks like. Here's 3, here's 7, and it's all the same height. And I want to go 4.7, which is about here, up to 6.5, which is here. And I want this area here. Well, it's a rectangle. I just need to know how wide it is and how high it is, and that'll be fine. So I know that this width is 4, and this height is therefore 1/4, because they have to multiply to give 1, and this width is whatever 6.5 minus 4.7 is. Well, 6.5 minus 4.5 would be 2, and we've taken off an extra 0.2, so that's 1.8. No, it's, yes, that's good. Just let me check that. If we go up 2, it would be 6.5. Yeah, okay, good. Okay, and so therefore the probability is this times 1/4, because it's the area of a rectangle. So just to do the full working, 6.5 minus 4.7, that's the width of the rectangle, which is 1.8. The height of rectangle is 1/4, and so therefore the probability of being between 4.7 and 6.5 is just 1.8 times 1/4, which would be 0.45, I think, because 18 divided by 4 would be 9 divided by 2, which is 4.5, and the 4 is in the first decimal place position. Okay. Or use a calculator, whatever. I like practicing my mental arithmetic. I'm really bad at it, relative to like my wife, who's a kindy teacher, and she's way better at mental arithmetic to me. Ask me to calculate something in terms of Q, well, I'm your man. Actually, an actual number, that's a whole other story. Okay. So I can't actually think of any specific situations where the uniform distribution is useful other than picking random numbers between two different zones. Yeah, because almost all real-life situations, some things are more likely than other things. The thing that makes it, I mean, in a probability course, it was like all about probability. You can actually create any distribution in a computer starting with a uniform distribution and doing some various transformations on the functions. And so that's one of the reasons why they include it. But it's also included in the course because it's a thing that you can calculate by hand, just by knowing how a probability distribution graph ought to behave. And so it's a problem-solving exercise more than a useful thing. So we use this to feel like we have power over our probability, and then we move forward onto the other things. The normal distribution. In case you're ever looking at these online, other places in the world, if you're looking for online videos from elsewhere in the world, other places in the world call this the Gaussian distribution. In case you're interested. It just might make other people, online resources from, say, the USA a little more comprehensible. So the normal distribution is, again, just picking a random number, but it tends to happen when you measure physical objects. So you measure a random object, and it generally produces a number, and that number comes from a normal distribution. There you go. That's not always true. The diameters of sand grains, for example, in, say, making concrete, do not follow a normal distribution. But most physical measurements of physical objects do. Diameters of sand grains follow the logarithm of the normal distribution. So, yeah, measure a random object. And what we have is that some things are more likely than others, basically. And x is the number measured. And it looks like this. It's not supposed to be fatter on this side than this side. It's supposed to be perfectly symmetrical. And somewhere in, and this thing is the mean. And the distance from the center to the inflection point is the square root of the variance. So basically, you're most likely to be near the number mu, and you get less and less likely the further away you are. So you're most likely to be near mu, you're less likely further away, and it's symmetrical. And this is our PDF here. There is a formula for this PDF. I've never known anyone to expect someone to remember the formula for the normal distribution PDF, but there is a formula for it, and just for your own edification, it's 1 over the square root of 2 pi sigma. No, crap, the sigma isn't under the square root. There you go. That's the PDF of the normal distribution. As described by Gauss, hence the name Gaussian distribution. And extremely frustratingly, there is no formula for the integral of this. And so if I want to calculate areas under this curve, which I'm going to need to do to calculate probabilities, areas are integrals. I would need to integrate that, and that thing has no formula for its integral. That's impossible. And so the only way to calculate it is to approximate it with like the trapezoidal rule or something. Yay! Or with like a fabulous power series. So, because, you know, e to the x has a power series, so we just sub in that, and you can do this fabulous Taylor series for it and integrate that instead, and that's, I think, how calculators do it, or how MATLAB does it. Back in the day before calculators, some very careful people carefully and painstakingly calculated the probabilities that go with certain, the CDF that goes with certain x's and put them in a big table. And if you look up any statistics textbook, you'll usually find a normal distribution table, and people would have to look up the table. And over in economics, they still teach people to look up the table because they think it's important, and because it's like, well, if I had to learn to do it, then you will have to as well. But I think that's probably a waste of everybody's time. And now this is on YouTube in the public domain. I'm very apologetic to you economics lecturers. I'm sure it has pedagogical value. Okay, that's the normal distribution. And the bugger is that it's so damned useful. Okay, it's difficult to calculate, but it's really, really useful because if you measure a random object, it tends to be normal, especially things on human beings, which is why it's so useful in medicine. And basically anything that changes because of a large number of competing factors usually ends up being normal. And importantly, I will get to this in a second, it doesn't just come up with measuring a random object, there's a second situation that comes up in. But before I get to this, the mean is mu, and the standard variance is sigma squared, which is, you know, unhelpful, but there you go. The point is that in order to tell someone which normal distribution you have, all you have to do is tell them the mean and the variance, which is why variance is so important to people, because so many distributions are normal. And so I can say that I might say something like x is distributed normally with a mean of mu and a variance of, in this course, do they put sigma squared in that spot, or just sigma? And in MATLAB, do you put the sigma or the sigma squared? Bloody hell. Okay, just be aware that in some places in the world, it's n mu sigma, e.g. in MATLAB. Actually, over in the first year statistics course taught by the School of Maths, which teaches this course, it's mu sigma. And I don't know why the same people are teaching two different things. But anyway, it's probably to match with your textbook. It can't be to match with MATLAB, which would, you know, be logical. Damn it, I've insulted someone again. Okay, so the normal distribution happens when you switch perspectives. So before, we had a Bernoulli distribution with a yes or no measured on individual people, and then we collected them together and we counted how many yeses or nos there were, and it turned into a binomial distribution. The normal distribution also happens when you measure anything and you do the mean of those things for a group. So you might have all these people and you might measure, you know, this one comes out as 1.8, and this one comes out as 2.7, and this one comes out as 2.7 again, and this one comes out as 1.9, and this one comes out as 2.1, 2.2, 2.1, and you might measure a number on every person, and that number has its own distribution. So for a single person, crap, I should have done this in a different order, but that's okay. For a single person, maybe you have like a number, you know, x equals, and that x comes from some distribution. Maybe it comes from a normal distribution like this. And then, so this is like what these people are. But then if you measure the entire group and you do the mean of these measurements, well, if I measure multiple different groups, they'll all have their own different means. And so I've switched my view. I'm not looking at individual people, I'm looking at groups of people. So the mean of the measurements, 1, 2, 3, 4, 5, 6, 7. The mean x bar equals whatever it is, equals some sort of number. This x bar has a normal distribution as well, but a different normal distribution. Like that, where n is how many people there are. So when we had a Bernoulli distribution measured on each individual person and we added up how many yeses there were, it turned into a binomial distribution. When we had a normal distribution measured on individual people and we averaged them, it turned into a new normal distribution. And one of the big things in statistics is that it doesn't actually matter if this is a normal distribution. If this isn't a normal distribution or just some other crazy distribution, you don't technically know what this distribution is, but if your n is big enough, it'll be approximately normal anyway. So the central limit theorem says, I don't know if you've been told about this, but I have to say it because I've said it now. It says that if you have individual people and there's an x which is distributed by who knows how, then when you have a group of people or objects, they might not be people, they could be screws or schools or instances of solar flares or whatever, and you measure the mean, then it will be approximately normal. That's the central limit theorem. So we've seen two of those situations. Our first situation was if you have a Bernoulli, and then when you do a group it becomes binomial. And now we have if you have anything, and if you do the average of the group it becomes normal. Sweet. And that's the other reason why the normal distribution is so damned useful. Because if I average anything, it comes out to be approximately normal as long as I've got enough of them. Okay, so I have a switch of perspective again. Even if you measure a normal distribution on each person, but you ask a yes or no question about the number that you have, it will turn into a binomial distribution when you do the group. So I could, just one final example, measure x on 15 people, and x comes from a normal distribution with mean 5 and standard and variance, 1 squared, like that. And now count how many have their value of x greater than or equal to 6 and call that y. And call that number y. Well, let's think about this. Each individual person has a number, which is x, but then that number is turned into a yes or no question. Okay? And so what we write down about each person is not the number x, but the answer yes or no, is x greater than or equal to 6? And so even though I've recorded a number on each person, the thing that I'm really interested in is the answer to this yes or no question. And therefore, when I do a group of them, there's 15 of them. And y is the number of yeses now. Well, since it's the number of yeses, it's a binomial distribution. I haven't done an average, I've counted how many yeses there are. And so my y is going to be a binomial distribution with 15 and some probability of getting a yes. So this is the thing I'm going to have to figure out. So to get a yes, there's 5. I would need my x's to be over in this zone over here, just there. And so I need to figure out what that probability there is. So that is my P. I may do this example properly. Why not? Just a second. Of course, you wouldn't write your exam solution with these pictures. You can put the pictures in, but then you'll do a proper version of it. Okay, so this is my plan. This is my reasoning behind it. I would actually, my working would go something like this. You know, for one person, the probability that x is greater than or equal to 6 would be this diagram here, which I know to be about 17%, but you would use your normal CDF thing. Okay, so CDFs are about areas, and PDFs, CDFs are about areas so far, and PDFs are about heights. I don't need to know a height, I need to know an area, but a CDF will only tell me the area so far coming in from this side. So I'm going to need that bit there, that's the CDF. So just a second, being less than 6 is the normal CDF, which I would need to look up the appropriate MATLAB for. What's the MATLAB for the normal CDF? It probably has CDF and norm in it, possibly in one order or the other. And I presume you put the number you're interested in and then the mean and then the standard deviation? Like that? Sweet. This is the bit I find the hardest to remember because I didn't actually do any of the MATLAB myself. But you may be asked, your lecturer, that won't be up here on the sound. You say, oh, but we can't do the MATLAB, but your lecturer may ask you what the MATLAB code needs to be. Or they may give you a list of various MATLAB codes and tell you what the answers are, and you choose the one that matches. How to do an exam that examines computer stuff without having a computer. And so the probability that x is greater than or equal to 6 must be 1 minus that. So this is approximately 0.17, by the way. Yeah, 68 on the inside, 34 on the outside, but only half of that is 17. And then we've got, what, 83. Okay. Sorry? Oh, you're totally right. Thank you. I'm using the information in my head, which is the outside. Sorry about that. Yes, these are what the numbers are going to work out to be. Sorry about that. Now, in my head, I know that between -1 standard deviation and +1 standard deviation is 68%. And so it must be 34 on the outside and 17 direct. So I can actually do this calculation directly in my head because it specifically had a number that I knew what it was. Okay, for one person it's that. And so therefore, y is a binomial distribution with 15 people and probability of success 0.17. Because for one person, so this is they're saying, therefore the probability of yes is 0.17 for one person. Right. So I just want to point out that just because your original situation had a normal distribution doesn't mean that when you put it into a group it's going to become a normal distribution. It only becomes a normal distribution if the thing that you are doing on the group is the mean. If the thing you're doing on the group is counting a whole lot of yeses, then that's what a binomial distribution is for. I was specifically asked when I did this seminar to talk about how to decide which distribution to use, and that's what I'm trying to get at here. All right. Oh, wow, my goodness. Okay, so, all right, so we have one more situation to look at, which has two distributions to go with it. Okay, I will just mention them. I'll do the mentioning of the situation twice. I won't do the whole spiel both times because I want a page for each distribution. But the two distributions I'm about to be talking about measure the same situation in two different ways. Okay. So the Poisson distribution, named after French dude Poisson. The Poisson distribution is discrete, and it's for this situation. So you have what they call a Poisson process. Where some event happens randomly in time or distance. So this is the picture I have. So this is when we start, and we have, event happens. Event happens. Event happens. Okay? And they're not equally spaced, they happen randomly. So it's possible that none of them will happen. It's possible that they'll be a whole lot close together. It's possible that they'll be really spread apart. So this is the start of time here. Okay, and you track over time or over a distance, and an event happens randomly in space or time. And cool, and you know how often it happens on average. So we know okay, so that will come as a rate, which is the number of events per unit time. Okay. Okay. That's the situation that we're in. All right? So what you actually measure, x is the number of events in a fixed interval. That's the important bit. It's not just the situation that tells you what the distribution is, it's the thing that you count or measure. And so when you do a Poisson distribution, you have x is the number of events in a fixed interval. And the thing that you need to describe everything you need to know about this distribution is how many events you expect in that interval. So it would be easier to do with an example, but I'm just going to draw my diagram. What tends to happen is it tends to look like this, and then it gets rarer and rarer for a heap of them to happen. And that sort of goes on forever. That's what my PMF looks like. So sometimes the 0 is higher than the next one. So sometimes it takes a while for it to come back down again. But in general, the last bit over here, it gets rarer and rarer to have that many in it. But not impossible. Okay, and so the height of this is, okay, second. And so the height of this is given by this. Let's see if I can remember this. The probability that x comes out to a specific x is, there's an exponential in it. This is where I look it up. Yes, you do. This is the one that came in last year's exam, and I'm pretty sure you get that as well. E to the minus mu, mu to the power of x over x factorial. That's the formula for a specific height. Okay. Where this mu, number of events you expect in the time, in the interval. Okay? The number of events you expect in that interval is what the mu is. The E is the number E. 2.7-ish. So, see that minus mu? That x factorial gets bigger and bigger the bigger x gets, and so the probability tends to get smaller and smaller. Okay, so that's what the Poisson distribution is, and you'd normally say that x was distributed according to PO? Sure. And you just tell them the mu. Is it POI? Just PO? I don't know. I don't think anyone will care. As long as you've got at least the P and the O, it'll be okay. Because just a P would be a probability. Okay. And in MATLAB, I think it's plus, POI-SS. I could be wrong about that too. Okay. So that's my POI. So I'd recommend adjusting my thing here and adding your MATLAB code to each one of these. Okay, so this is enough to describe to a statistician everything we need to know. And that's pretty much it, but it's easier to see how these things work out in practice with an example. And beware of perspective shifting. Just like with our normal distribution, I can switch perspective and turn it into a different normal distribution or into a binomial distribution. I can perspective shift on a Poisson process as well. So I can say, let's see. A possum will run across the roof on average once every 2 hours. Yep. Yay. What is the probability that will happen less, more than 3 times in, I mean, how many revision seminars did I do? 1, 2, 3, 4, 5, 6, 7. 18 hours. There we go. So a possum will run across the roof on average once every 2 hours. What is the probability that it will happen more than 3 times in 18 hours? Okay. So any probability question, when it says what's the probability, you need to decide what all the options are and how likely they are, which means I need to describe a distribution. And so I'm looking at this and I have an event that's happening randomly in time. I'm assuming it's random. And I know how often it happens, and that's enough to be a Poisson distribution. So let's assume it's random in time, and then we expect 1 1 in 2 hours, and so we therefore expect 9 in 18 hours. That's what we expect. And so I'm going to say let x be the number of possum runs in 18 hours. Then x will be distributed as a Poisson distribution with mean 9. Because I expect there to be 9 in the 18 hours because there's 1 every 2 hours. Okay, and what I want, so far what I've done is I've looked at my situation and I've decided what distribution describes the thing that I'm measuring, and I've actually declared what variable to be the thing that I'm measuring. And I've called it x, because that's going to allow me to convert the question I have into probability notation. I want the probability that x is greater than 3. Okay, I'm just going to do some imagining. 0, 1, 2, 3, 4. Etc. I want this bit, the bit that's greater than 3. Okay, so I'm adding up multiple probabilities. Okay, so I could imagine figuring out the probability for 4 and 5 and 6 and 7 and, oh damn, I have to do it infinitely long. So that's not going to work. And so the easiest way might be to go, well, the entire thing is 1 and take off 0, 1, 2 and 3. That would be the way of doing it by hand. But on the other hand, if I have a computer, I can get it to calculate these things for me. So I'm going to say this is the same as the probability that, damn it, it's 1 minus the probability that x is less than or equal to 3. That's a minus sign. It's just really emphasized. Okay. So my picture helped me to imagine that. And the reason I did less than or equal to 3 is that it's specific numbers, and I want to include this one. In general, the opposite of greater than is less than or equal to. But just be careful when you do this sort of thing, that if I had asked for greater than or equal to 4, then it would be x is strictly less than 4, which is the same as less than or equal to 3. But that's only because this thing can only produce whole numbers. Okay, so the easiest thing is for me is to draw the diagram and read what it says. Okay, and this would be 1 minus, how do you write, I don't know, whatever it is. Just a second. Like that. So you put the number that you're thinking of and the mean. And I know it's a CDF because it's adding up multiple possibilities. My computer isn't capable of doing an upwards CDF. It has to do downwards. And so that's how it's done. But if I wanted to do it, that's in my computer version. My by hand version would be to take off the 4 possibilities. So my by hand version would be e to the minus 9, 9 to the 0 over 0 factorial, e to the minus 9, 9 to the 1 over 1 factorial, e to the minus 9, 9 squared over 2 factorial, e to the minus 9, 9 cubed over 3 factorial. That's my by hand version. Yep.
So you use that when it's less than or greater or whatever, but if it's asking x, just how many times x is equal to 3, you just use 3 as the...
That is a most excellent what-if question. Let me write that down. what if I asked probability of exactly 3 Poisson runs? In which case it would be the probability that x is exactly equal to 3, which is just that specific number. And so in terms of the diagram, it's just that one. And so that would be plus PDF 39 in a computer. Or by hand, I would just go e to the minus 9, 9 to the 3 over 3 factorial. Well done. I do like a good what-if question. It helps us to understand what's going on. Okay, that's the Poisson distribution. But beware of perspective shifting. If I suddenly now said, what's the probability of more than one in the first 5 hours, then I've changed my time period, and so I've changed my distribution. Because in a longer time period, you would expect more of them to happen, and so the probabilities will all be different. And in a shorter time period, you expect less of them to happen. So now we expect 1 in 2 hours, and so now we expect, 2.5 in 5 hours? Yeah, that'll work. Essentially, it's, you just go this divided by, the time period divided by how many you expect in 1 hour. And so let y be the number of runs in 5 hours, and so therefore y will be a Poisson distribution with mean 5 over 2 now. And so all my probabilities will be different than they were before. And so the probability that y is greater than or equal to 1 will be the same as the probability that y is less than, more than 1, sorry, strictly greater than 1. It's less than or equal to 1, which is, damn it, 1 minus that. CDF of 1 and 5 on 2. Or if you want to do it by hand, it'll be 1 minus, just a second, 0, 1, 2, 3. So we'll take off the 0. So what was it? E to the minus 5 on 2, 5 on 2 to the 0 over 0 factorial minus e to the minus 5 on 2, 5 on 2 to the 1 over 1 factorial. So it's possible that this sort of thing will happen in the same assignment or exam question, that you've got the same situation but it's been measured in 2 different ways, and so there's 2 different distributions. All right. I have one more distribution. Which is the exponential distribution. And the exponential distribution is the same situation as this, but measuring something different. So the exponential distribution is continuous. That's not important. The exponential distribution is continuous, and it goes with the same situation. We have events occurring randomly in time or distance. We know the rate. Okay, it's still a Poisson process. And we know how often they happen. So you might see it as rate per unit time. You know, the number of events. But you may also see it the other way around as the time per event. So this thing is usually called lambda. Pretty sure. Yes. No. For this. I'm just going to look up the notes because I always get this wrong. The mean time until the event occurs. No, this is lambda. Lambda is the number of events per unit time. Right. This as yep. But MATLAB calls, so be very careful. MATLAB calls this mu for the Poisson distribution, and it calls this mu for the exponential distribution. Just be careful. Okay. All right. So this is it. And the thing that we measure is the number, is the time until the next event. So when I have my thing here, I'm measuring the time until the next event. This is what x is here. Whereas the Poisson distribution was how many events there were. So in the exponential distribution, actually the events themselves are what tells me what time frame I'm looking at. I don't have a fixed time frame. So over in the binomial distribution, I have a fixed number of trials, and I count how many times something happens. I really wish we had another distribution in this course, which is called the geometric distribution, which is I do something over and over, and I just count how many times I have to do it until the thing I want happens. So, you know, I roll a die, and I go, how many times do I have to roll it until I get a 6? That's sort of this situation. Okay. Sweet. And this is a continuous distribution. And it has the tendency to do this. It can be really spiky at the front here. It can be something that really likely to happen very fast, but in general it gets much less left. Nope, I'm completely wrong. It's this shape. Sorry. It's always this shape. Sorry about that. So this is the PDF. I was wrong. I was thinking of the chi-square distribution. Okay. And interestingly, when we do the exponential distribution, we often calculate how far it is to be further out. So, just so we know, the PDF is f of x, which is lambda e to the minus lambda x. And remember, that's number of events per unit time. And the mean. So this is one of the few ones where it's extremely useful to know the formula for the CDF off the top of your head. So all the other ones, you're just told what the PDF is, and that's enough to do what you need to do. The CDF for the exponential distribution is extremely useful to know. Let me just see if I can. So capital F of x, which is the probability that x is less than or equal to x, is 1 minus e to the minus lambda x. And in fact, the easiest thing for me to remember is that the probability that x is greater than a specific number is just e to the minus lambda x. Like that. That's e to the minus lambda x, this area here. This one is this way. This is the simplest of any of the formulas we have, that one there, and that's the easiest one I find to remember. Okay. And the mean is 1 over lambda, which is time per event, right? If lambda was event per time, then 1 over lambda must be time per event. And the variance, for the sake of... Do I have an actual one that's sharp? No. I have to sharpen a pencil. Might need to, because all these pencils seem to be broken all the way down. Here we go. The variance is also 1 over lambda. And just warning, in MATLAB, you'll do the exponential CDF of the x and the 1 over lambda. Okay. All right. Sweet. Okay. So this is the same situation that the Poisson distribution happens in, and it's therefore likely that if you're given a specific situation that's events happening in random or space of time, you can get both questions about both of these distributions. And you'll need to give them their own letters so that you can do them. Yeah. So I might need a pen. I don't want to do that. How long into? What is the probability not run across the roof until after the first hour. So, I mean, obviously, since I'm doing this in the exponential distribution part, it's going to be an exponential distribution. But imagining that you started with this and you didn't know that already, you would go, okay, I'm talking about the probability of something happening, and the thing that's happening is about the time when the event happens. Okay, this is about it's about the time until an event, which is what's telling me that it must be an exponential distribution because that's what the exponential distribution discusses. Okay? I haven't got a fixed amount of time. I've got the first hour, but I'm saying if I could figure out in advance how long until that first possum run, and just see if it's more or less than an hour, then I'll be good. So what I'm actually going to do is I'm going to say let x be equal to, just be aware that if you're doing this as part of a big question and you've already used x, you might want to pick a different number, a different letter. So I shall use t because it's a time. Let t be the time until the first possum run. Then t is a Poisson not Poisson, crap. T is an exponential distribution with, now just a second, what was the rate? The rate was 1 every 2 hours, right? So we need to do it as an actual speed. So this one here, it was 1 every 2 hours, and so therefore the rate is 1 2 events per hour. Okay. That makes sense. I mean, if it takes 2 hours to get one event, then in 1 hour you would get half an event, on average. And so, therefore, I want the probability that the time is more than 1 hour. So the time until the first possum run happens after the first hour. So the time is more than an hour. So if you were doing this in a computer, you might think, all right, probability t is greater than 1 is 1 minus the probability that t is less than or equal to 1. Which would be 1 minus the exponential CDF 1, and we go 1 over the half that we did here in order to get MATLAB to do it properly. So this has to be the 1 over lambda for MATLAB. Okay, sweet. But by hand, P of t greater than 1, well, we've got a formula for that directly. It was there. Either minus lambda times the x that we're thinking of. And so it's just that, which is whatever it is. 1 over the square root of e, whatever that is. I could calculate that. Google can tell me that. .607 to 3 decimal places. Yay! Okay. And you know, we could do a full-on double bluff and say, okay, in the 9 revision lectures, how many of them will have a Poisson run before an hour, after an hour, and now I'm having a yes or no for 9 objects, and it's a binomial distribution. So I can turn anything into a binomial distribution if I want by turning into a yes or no question. So that's all the distributions in this course. And I don't feel bad for not talking about the other stuff because it is all on the revision seminars on the website somewhere, including the one I did on the Frobenius method for differential equations 2 yesterday, but that's not there yet. That'll be there at some point today. Yes, and I am going to stop there. Unless someone has another question about probability distributions which would reasonably go on this video before we go.
What happens if the Poisson has already found the right 3 times and then it turns out that the chances of the Poisson
So that's an excellent question. So feel free to go if you want, but could you do it quietly so that I can answer that question? Please. Thank you. So what if you already know that it's happened like twice? Is that the question? So I need to sort of translate that into, so I'm going to do 2 of them, right? Just a second. What if the event events happened twice already, and I'm interested in how long it's going to take until the next one. That's one thing I could do. The events happened twice already. What's the probability that I wait until the third one? And the answer is the same. Okay, so previous events are independent of future events. So the probability 1 hour, oh crap, more than an hour. Greater than or equal to 1 hour until the next event is the same as it was before. If it was a Poisson situation, and I already had 2 events, and I want to know, that's a whole other thing. Let me just think about that. E.g., so looking at 18 hours, we know there's 2. What's the probability of 3? That's a whole different situation. I'm thinking that that's the probability that my x is greater than or equal to 3 or more. 3, given that x is greater than or equal to 2.
Isn't Poisson memoryless as well?
Sorry?
Isn't Poisson memoryless as well? Like it doesn't affect?
I don't know. I'm going to give it a go. So what's the probability that x is greater than or equal to 3 given that x is greater than or equal to 2? I mean, that's what this says. We know that there's at least 2, and we want to know if there's at least 3. I mean, if we know there's 2 so far and we know what time it is, then we can just do the Poisson from that point forward and it's a new distribution. So I don't think the Poisson is memoryless because if you know that it's happened something's happened in the first 2 hours and you're now looking at the second 2 hours, then you're not looking at 4 hours anymore, you're only looking at 2, and so the distribution has changed because the time period has changed. I'll think about that as well. But for the moment, I'm just going to do this. So this would be the probability that x is greater than or equal to 3 and x is greater than or equal to 2 out of the probability that x is greater than or equal to 2, because that's how you do conditional distributions. And being more than 3 and being more than 2 are together just the same as being more than 3. Like that. And so this would be 1 minus and this would be whatever they are. Which I have a feeling is not going to be the same answer as just greater than or equal to 3. Because I have changed the knowledge. I know how many events have happened. I know there's at least 2. But I think you might be thinking of this situation. E.g., we know 2 possum runs in the first, 5 hours. What's the probability of at least 3 total in the 18 hours? That situation. So here's my time. Here's 5 hours. Here's 18 hours. And there's 2 events here. And we want to know how many are here. And so the thing is that what happens in these first 5 hours shouldn't make any difference to what happens in the remaining 13 hours. And so what we're looking at is that looking at the last 13 hours. And so we expect 13 over 2 events, because they happen once every 2 hours. And so let Z be the number of events in the last 13 hours. And we want the probability that Z is greater than or equal to 1, because we needed 3 total and we already had 2. And that would be 1 minus 0, 1, 2. Okay, so that's just the first one. So we only have to take off 0. So technically that's plus PDF of 0. We could have done CDF and it would have been the same answer.
Can you page up?
Yes, I can. So that would be, because it's just this single one, I can do it as a PDF instead of a CDF. But if I had done CDF, it would have been the same answer. Yeah. And that would be just 1 minus, now what is it? E to the minus mu to the 0 over 0 factorial. Which is cool, because that's just 1 minus e to the minus 13 over 2, because that's 1 and that's 1. Which you may notice is the CDF of the exponential distribution. Because this is the same question as if you want at least 1 event in this time, that's the same as saying that the time until the first event is earlier than 13 hours. And so you can do it as an exponential distribution instead if you want.
I've noticed in the exams they do give you Poisson or exponential.
Yeah. So I could have done, or let t equal and time until the third event from 5 hours on, and then t is an exponential distribution with rate still 1 in 2. And so we want the probability that the time until that event is less than 13 hours. Since need first event before 13 hours. And so you could have done that as the exponential CDF of 13 and 2. And that would be the same answer. 1 minus e to the 13 times a half minus a half times 13, which is the same thing. Yay, and the world makes sense again. So you get to choose, if you can pitch it in terms of time, and if you can pitch it in terms of events, then you get to choose whether it's Poisson or exponential. There we go. That was good. That was some great question. Well done. No, you. Multiple people. Yes?
I have one more quick question.
Uh-huh.
Originally, when you did the Poisson distribution, when you were saying about the rate, you said in 1 or 2 hours. If you were to change that so the rate would be 1 in 4 hours or whatever the case, so it would be a quarter. And then when you said, when you were doing the exponential, you said what is the probability that a Poisson will not run across the roof? So would that mean because if you want for it to run, and now you're asking what it will not run, well then you have to go 1 minus a quarter to be the lambda, because you're changing.
Let me just think about that. So this one here, what is the probability that the propulsion will not run until after the first hour? Is that one? That's one you're talking about?
Yeah. So originally you said that the rate would be 1 over 2 with the Poisson that will run. So I'm
Yep.
saying if the rate was changed, so
One every 4 hours, yeah.
for it to run, does that mean that when it will not run, it will be 1 minus that rate?
No. It stays the same, and you're right, the half is a bit confusing because 1 minus a half is the same as a half. Good pointing out. It's the same. I will write it down properly. Because I converted this not run until after the first as running. It's not running until after the first is the same as running after the first. Not run until means that the event happens after that time. And so I actually converted it into a statement about the event happening, and that meant I didn't have to worry about any of that. Cool. Good being wary of the toast there. You're welcome.
Did you say that there's DE videos online? Had you already done a revision lecture for DE?
I did it for a different course,
Oh, okay, right, cool.
but it's similar stuff, so I'll put it up there anyway.
That's kind of just the maths.
So if you go to the Maths Learning Centre's website
Yeah.
and you go to resources,
Yeah.
there's a page for Eng Maths.
Okay, perfect.
And it will look a little differently to this when you get there because I'm rearranging it, but there's all these videos on DEs and it says what's in each one.
Awesome. No, that's great.
Yeah, so I haven't put the one from yesterday up, but there is already one on Frobenius.
Anyway,
And there's like 3 or 4 on separation of variables and PDEs.
that'd be awesome. Lovely, thank you.
Could I take a look at your original Poisson distribution question? Just want to double check something. The example. Yep, this one. So let's say the question is asking what's the probability that it will happen more than and equal to 3 times. So this will have a line under it. So
Yeah,
will
yep.
this be x less than equal to 2?
Let me do that. I'm just going to have to text her it is. So what if we want probability of at least 3 times, yeah?
Yep.
Then we've got x is the number of times. And we need the probability that x is greater than or equal to 3. It's supposed to get shorter, but really it doesn't matter. So greater than or equal to 3 is these ones.
Yep.
Okay, so that should be 1 minus the probability that x is...
Less than equal to 2, right? Okay, yep.
Now, if I was doing this with a normal distribution, I wouldn't do that.
Oh, really?
So if I had like y is a normal distribution of mean 5 and standard deviation, 1.3, and I said, what's the probability?
Oh, are you just making up numbers?
Yeah,
Oh, okay.
it's random thing. What's the probability that the measurement is at least, 6.7, just random numbers, then that would be the probability that y is greater than or equal to 6.7. So there's 6.7 here, and it's this bit.
Yep.
And we want, the CDF is this bit. We can go all the way up to 6.699999. And so I don't go down to something else. Even if this was a whole number and it was just 6. It's not less than 5, because it's possible to be 5.5 and 5.8 and 5.9, and I have to make sure I include all of those possibilities.
Okay.
But for a normal distribution, this is the same as that, because I can go all the way up to 5.999999. So being less than 6 is the same as being less than or equal to 6. Because the 6 itself, because there's infinitely many possibilities, doesn't make much of a difference.
Okay, so we need to see whether it's discrete or...
Yeah.
I see.
And that's why I like drawing my diagram, because it helps me know what to do.
Yep, got it. Okay, thank you.